3番目は、
The third presentation will be made by Professor Peter Englezos, the Department of the Chemical and Biological Engineering, the University of British Columbia. And the title is The Gas Hydrates and Carbon Management.
Thank you, Professor Mori. Good afternoon, everybody. I'd like to thank you for the kind opportunity to come and present here at this forum, and also to renew ties with Keio University. I will briefly touch upon the subject of gas hydrate. We've had a number of wonderful talks so far. So what I will do is I will remind you about the need for carbon management that arises from a necessity to establish a more symbiotic relationship with the Earth, and in doing so, also what the role of gas hydrates is going to be. So very briefly, the story of gas hydrates, in my view, starts 200 years ago at the Royal Institution in London, and it's attributed to Dave and Faraday. And very briefly, what you see in the picture here, you see a water droplet that is exposed to an atmosphere of methane and propane, and under suitable temperature and pressure, it transforms to, I'm sorry, the wrong button here, it transforms to this powder, which is the gas hydrate. And we've heard this morning from Anne Arcan and Leslie Gill about naturally occurring hydrates in many parts of the world. In fact, they're more or less evenly distributed, unlike the distribution of conventional oil and gas. And there are many locations where people have actually identified gas hydrate, and that is believed to be a potential source of natural gas. And as we saw this morning, the concept was we were able to prove the technical feasibility of this project as a result of the collaboration between Japanese and Canadian researchers. So what remains to be done is to move towards commercialization by demonstrating a sustainable flow of gas from a producing gas hydrate reservoir. Now, let me now turn to the attention of carbon management. Very simply speaking, our society relies more and more on fossil fuel energy. And as we heard before this morning, I was surprised to hear that over the past 30 years in Japan, the energy consumption was tripled what it was 30 years ago. So we're using a lot of fossil fuel energy, and in doing so, we're generating carbon dioxide. Just a figure here, about 25 gigatons of carbon dioxide annually we're emitting. And there is an emissions problem there that is linked with the enhancement of the already existing greenhouse effect and the resulting climate change. So what we have done so far, we're now realizing that this path of development is no longer sustainable, in the sense that the Earth is a finite system, and now we are exceeding the carrying capacity of the Earth. And so clearly we're tipping the balance. And therefore, what we need to do now, we realize we need to transition to a situation where our relationship with the Earth will be symbiotic and sustainable. And in order to do that, it is believed that we have to change the energy, the way the source of energy, or the way we use energy. And part of this is the need for carbon management. In fact, if you look back in history, we are already in a path of actually deriving our power from less intensive carbon sources. Essentially, if you look at the dominant source of power from coal to oil to natural gas, there is less carbon per gigajoule of energy obtained. However, what has changed over the years is the overall amount of power and the needs. So overall, the amount is just growing tremendously. So we are already in the path of decarbonization, and the idea is to move towards a carbon-free or less carbon-intensive world. So as I said, what the vision is to a more symbiotic relationship with the Earth so that we can continue enjoying the benefits of our civilization. So in this vision, our footprint should be compatible with the Earth's ability to sustain us. And that's a real challenge. And the way we envision it, because we're not there yet, there's a long path that lies ahead. People envision a closed-loop economy that is, you have energy and material integration, so nothing flows out of this system. So recyclability is a concept there. And the dominant energy carriers would be what they call green electricity, solar, and green biofuels. So what is the role of clathrate hydrates in this vision? We've heard just in the previous talk the role of hydrates in developing gas hydrate-based technologies. We also heard from Professor Mori this morning. And I want to use this term about technologies, a set of materials, tools, and devices and procedures that predictably and reproducibly combine to produce a specified desired effect in the material world. So what could be the role then of hydrates? Well, depends what choices we have to make and how quickly we advance the development of renewable technologies. So it is conceivable that a completely transformative technology will appear because humans have demonstrated that they rely on ingenuity when they are pushed to the corner. They can come up with key concepts. So it is conceivable that a revolutionary concept appears that basically renders fossil fuel energy redundant. But the most logical path, in my view, or the most possible path, would be a gradual transition towards this sustainable path. And gas hydrates can clearly play a role in a number of ways. First, as a potential source of natural gas type energy, and it is now believed that this may be realized over the next 15, maybe 20 years as a result of activities such as the Japan-Canada collaboration. And in my view, there is also the potential for utilizing gas hydrates directly or indirectly in a number of technical areas. And I listed there the most predominant, and that is carbon management and natural gas transportation and storage. And we just heard in the previous talk the evolution of the ideas in the area of natural gas storage and transport. So I'm going to focus on CO2 management. And just a couple of slides to remind you, there is a tremendous need to deal with existing power plants because the combustion of fossil fuels generates flue gas, which if you can treat is essentially a mixture of carbon dioxide, nitrogen, and oxygen, and there's a bit of SO2 there. And essentially what you want to do, instead of emitting it into the atmosphere, you want to capture that CO2, and then you have to do something with it. You have to sequester it. So that's what they call post-combustion capture, that is capturing the CO2 from power plants that have been built over the years without taking into account what we have done, that is to disturb the balance with respect to our symbiotic relationship with the Earth. There is also another concept that emerges, and that is to remove the carbon from the fuel before you actually combust it. And essentially, you create another energy carrier, which is hydrogen. So you utilize hydrogen. But again, this concept will necessitate the need for capturing the carbon. But this time, you're going to be dealing with a different kind of separation of CO2 from a CO2 hydrogen mixture. So in both cases, there is a need for separation, gas separation technology. And gas hydrates can be one of those concepts that can be considered because essentially if you mix water and one of these gas mixtures, what will happen because of the molecular phenomena there is that you're going to end up with a hydrate crystal that will be enriched in CO2. So CO2, to put it simply, likes to be in the hydrate crystals, as opposed to the rest that likes to stay in the gas phase. So conceivably, then you have one stage of a separation into two streams, one that is rich in CO2 and the other is depleted in CO2. So that's the idea behind. And what we've done over a couple of years in the laboratory, we were able to demonstrate that you can actually begin with such a typical flue gas mixture. And what we were able to do is add a little bit of another hydrate former in order to make the pressure conditions more achievable. And that has a huge implication in terms of the compression cost. Because, I'm sorry here, because you have to remember that the flue gas exits the power plant at atmospheric pressure. So you need to compress that. And what this work demonstrates that after a stage of hydrate formation, you end up with a hydrate that is enriched considerably in CO2. And what you can do is you can gasify this hydrate and go into a second stage, reform hydrate, and you end up enriching the CO2 further. You can go up to 90 plus CO2 with a third stage. Now, people believe that if you're able to separate a flue gas up to a 90% CO2 content, that would be a reasonable enrichment. There is no need to go beyond that. The cost is just becoming too tremendous. And at this point, I should remind you of actually other technologies that exist out there. We know very well that in the natural gas industry, we're able to separate CO2 from acid gases through physical or chemical adsorption. So these are two other methods that are actually working in industry, but they have not been able to make them work under economic conditions under such a huge scale that the power plant demonstrates. And you need also to introduce another gas separation technique in this block flow diagram, and we thought that a membrane separation process will deal with the CO2 lean stream. Now, this was demonstrated, obviously, in a lab scale. It's not a continuous process. And if you do some quick estimation about implementing this concept into a power plant, you'll need a tremendous amount of power to run this. It's simply compression cost. So it's a lot of parasitic energy there that this will be required. So clearly, there is a need to actually reduce the operating pressure primarily if you want to advance this concept further. And that's why it is still at the research level, in my view. Now, this is a more interesting concept. That is the precombustion concept. Essentially, you can still use fossil fuels, and through a gasification or a reforming process and the shift conversion, you end up with a fuel gas mixture. So you have your energy carrier, that is the hydrogen. And now, through gas hydrate crystallization, you're going to separate it from the CO2. And why this concept is attractive? It's attractive because that CO2 hydrogen mixture actually exists already under high pressure conditions. So there is no need to pressurize and consume electricity. It's already under high pressure, which is what you want in your hydrate formation reactor. So that's a real benefit. So we did some laboratory investigation. So we formed hydrates under two different pressures, shown here, 7.5 and 8.5 megapascals. And what happens is, starting with a 40% CO2 mixture, you end up forming a hydrate with 86% CO2. So there is tremendous enrichment in the hydrate. And based on that, what we did is we did obviously a series of experiments in the laboratory to demonstrate that you need actually two stages of gas hydrate formation in order to enrich the CO2 stream to 90+%. And again, you would need an extra gas separation unit, not a hydrate unit this time again, to deal with the CO2 lean stream. It turns out, if you do some quick calculations, that the compression costs are not really huge, even in this process, because, as I said already, the gas mixture is under high pressure. We demonstrated this in 0.3 and 2 liter reactors. Again, it's not a continuous process, but in my view, it's quite promising, actually. It's still at the research level. Again, you're competing against gas absorption, which is an industrially established technology in the natural gas industry, but not yet in the power plant CO2 capture area. So there are some issues that need to be resolved if you want to move forward. And the first one is to look at the hydrate formation vessel, where there is a need to switch to a continuous operation. You need to look at the way you contact the gas and the water. You need to do that more efficiently and also remove the heat of the crystallization. Scaling up is obviously the other trend, and always look at the economics and compare with competing technologies. So we've looked at the reactor and the contact mode, and the previous results were all obtained in a classic stirred vessel type system where you have water and gas and you agitate to mix them. An alternative concept is to have a water and just silica sand, which is really a porous material. And we got this idea from naturally occurring reservoirs or hydrates that actually were formed in the earth in this type of environment are the best candidates to be exploited for natural gas recovery. So we did the experiments under similar conditions, and we wanted to compare the speed at which we're forming hydrate. And indeed, we realized that the speed in this porous media type or fixed bed reactor is quite enhanced compared to the speed in the other reactor. So that's a good thing. You're forming hydrates faster. We also looked at the water conversion into hydrate, and we tested a number of systems. Obviously, the CO2 hydrogen, CO2, and then a natural gas mixture type system. And in all cases, if you look at this dark bar, it represents the water conversion in the fixed bed reactor compared to the stirred vessel, and it's always better. So there is a little bit of improvement, in our opinion, in this area. Now, capturing the CO2 is one thing, and in fact, as I said, there are a number of competing technologies. None of it has been established yet, although the prevailing thought in industry is that gas absorption most likely is going to be the best candidate that will be tried out. But you have to do something with that CO2 once you capture it. There was a lot of discussion in the past 10, 15 years about ocean sequestration. I always thought that's not a good idea. In fact, I thought it was a crazy idea to put CO2 into the ocean because of a number of reasons. First of all, you will enhance ocean acidification, which is already happening, and people haven't paid enough attention as they should have paid to it. And plus, CO2 hydrate eventually is going to reach an equilibrium system, so some of the CO2 is going to be removed. I think, in my view, the future is in geological storage, and you can do that in a number of ways. The most attractive concept, in my opinion, we heard this morning in the NRCan talk, is the CO2 methane exchange mechanism. As you saw the map with all the natural gas hydrate locations, the idea and the concept is to inject that CO2 in selected reservoirs that already contain natural gas, and because of the thermodynamics, it is conceivable that you will replace the methane molecules with the CO2 molecules. So you're not only sequestering CO2, you're recovering methane. It's a great idea and concept that deserves a bit more attention. And we began looking into this in our laboratory. Another idea is to look at depleted gas reservoir. And this is something that I'm looking into with some collaborators from Alberta to actually inject liquid CO2 into this abandoned natural gas reservoir. What will happen, what you expect will happen, is that as you pressurize that abandoned reservoir, there's water there. This is a wet reservoir. There's methane, some methane. Eventually, you're going to reach a point well, your CO2 will form some kind of hydrate, either with methane or by itself. So it remains to be investigated. So that brings me to offer some concluding thoughts. And I will just focus on the hydrates and the role in CO2 management. Clearly, there is merit to utilizing the gas hydrates for capturing CO2, particularly in the area of CO2 hydrogen separation because of the beneficial conditions at which the mixture comes out from the gasifier. We've demonstrated that in the lab, but there's work to be done in order to move into a continuous operation. Clearly, there is some progress in the area of the type of reactor that you need to use. You move into a stationary reactor, and the benefits there are, as we saw, increased speed, increased water conversion. Also, there is no need for agitation of the water mixture. That agitation, you can do it in the lab, and you can sort of ignore the power required to run it. But if you want to scale it up, that's going to require a tremendous amount of power, and clearly you need to move away from that and avoid using so much power. You have to do something with the CO2 that you're going to capture, and no matter what technology you're going to utilize, whether it is based on hydrates or amine absorption or membrane separation, it doesn't really matter. You have to deal with that CO2. It seems to me that sequestering that CO2 in depleted gas reservoirs or in depleted or in other geological formations is a logical step, and most likely we will see that. There's a lot of work that is done actually in Western Canada in this area. A more interesting concept that deserves further attention is this CO2 methane exchange that I talked about, and I suspect we're going to hear more in the future. So that concludes my talk. I'd like to thank you for your attention, also thank my collaborators, particularly Dr. Ripmister's laboratory in Ottawa that gives me the opportunity to combine my engineering approach to studying the problem with the molecular science that Dr. Ripmister's lab offers me the opportunity to work on. Thank you again for your attention.
ありがとうございました。じゃあカーボン
Thank you for your presentation. Carbon dioxide, carbon management were the focus of the speech. Any questions or comments from the audience?
じゃあちょっと座長の方から一つも。I have one question, simple question.
I'd like to ask a question.
You talk about the possibility of using the fixed bed reactor. It is very interesting, but my question is that how do you think about the possibility of scaling up of such as a stationary reactor? If you say enlarge the scale of the fixed bed reactor, I think that the heat removal will be very difficult because of there is no convection. Some comment?
I don't disagree. I agree with you. I agree with you. But at the end of the day, this is a technical problem that requires some ingenuity, whereas the agitated reactor, to me, is a bit of a dead end because the power requirements are enormous, and at the end you don't want to have the power plant producing parasitic energy to such a large extent. Because if you remove yourself from the situation, and if you see why are we not advancing fast enough in this area of carbon management, there are two reasons, and they are interrelated. One is economics. Yeah. I mean, you don't want to lose 50% of your power just to capture the CO2. And the other is policy, but they're both linked. I can't give you the answer. I agree with you. It's a real challenge. It's going to be a big problem scaling it up.
Okay, thank you. 他にいかがでしょう?
Thank you for your response. Any other questions or comments? Professor Ueda.
Thank you very much for your interesting talk. And I'm interested in the pre-combustion reforming, the separation of the CO2 from the reformed gas. So that is very nice idea, because if it is very difficult usually to separate the CO2 from the reformed gas, and we need to use a very expensive membrane, something like that. But when we think about the use of fuel cell, something like that, so sometimes CO, carbon monoxide, has a very serious problem. Can we separate the carbon monoxide as well as the carbon dioxide in this way?
Presumably the carbon monoxide has been converted into CO2.
Yeah.
If there is some remaining CO there, I don't know. I think Professor Ripmister has done work with carbon monoxide. It forms hydrate, doesn't it? It does.
Yeah, thank you very much. That's very interesting. Thank you.
Thank you.
他にはいかがですか?
Any other questions or comments from the audience? CO2, methane replacement is also a very hot topic recently. It may be handled in the panel discussion. Thank you for your presentation. Let's move on to the next one.